Edoardo Lauria with a talk Strong Weak Duality for One-Dimensional Long-Range Ising Model. The floor is yours.
Thanks a lot. Well, it was beautiful to be here for the first time, and I really enjoyed this week in Cambridge, so thanks a lot for organizing this nice workshop and for inviting me to speak. I hope you can hear me, but you just do something if you want to hear me, but you can't. And okay, so my talk today, which I emphasize is the last talk, so I'm going to try to be very light eventually, and so it's about indeed some strong weak duality for the one-dimensional long-range Ising model. It's I believe a nice little story, and it's based on work in collaboration with Dario Benedetti, Dalimin Masac, and Philine Van Vliet, who is just there. So let me start with some review, just some review about this old story. So actually, first I'm going to introduce the model. So what is the long-range Ising model? It is a model of say classical spins, say on a d-dimensional square lattice, with long-range interactions. That means this is the classical Hamiltonian. It is a sum over, say, all the possible classical spins at positions I and j on the lattice, interacting through a potential that depends on the distance between the lattice points and depends on some parameters. One is d, the dimensionality of the lattice, which we take to be, say, bigger or equal than 1, and then s, which we refer to as the long-range parameter, which is a non-negative number. So you see, as you can see, I mean, this is different compared to the more standard short-range Ising, because here we are really coupling all possible spins and not just the nearest neighbors. So I'm not going to really use this lattice description, but except in a few cases. But in general, we are going to be interested in the universality class. Okay, so we'll be working in the continuum. But let me mention that, in a sense, this model has quite a few interesting properties. So first, it has a phase transition with spontaneous symmetry breaking of Z2. This is similar to what happens, of course, for the short-range Ising. But in this case, this spontaneous symmetry breaking is even possible in 1D for S smaller than 1, thanks to the fact that it's long-range. So this phase transition is controlled by some conformal field theory, and with the S-dependent critical exponents. So there is some non-trivial dependence on S in the critical exponents, and because of this non-trivial dependence, this model has the so-called feature, the so-called crossover from long to short range universality class, which is, you can understand, I'm going to tell more about it, but it's essentially the fact that if you take S to be big enough, right, this model is essentially, this Hamiltonian becomes effectively strongly peaked around the short-range coupling, and therefore you expect the long-range, the universality class to be that of the short-range Ising, right? So there are also a lot of beautiful connections of this model to interesting systems that are relevant for condensed matter for condensed matter. I'm not going to really use it, but I think it's interesting for the experimental reason, and for the theoretical reason it's interesting because this is perhaps one of the simplest examples of non-local conformal field theories, and of course it's related to, it can be understood as a defect theory. I'm going to to explain a bit of this, but it's a very interesting playground. So let me start by reviewing a bit the story about the crossover transition that I mentioned. So this is, say, a well-established diagram that you can obtain after, say, Monte Carlo, many years of Monte Carlo simulations. Okay. So the idea is that the nature of the long-range Ising universality depends on S. And just to fix ideas, let's imagine we start with a two-dimensional long-range Ising. So we just start with a two-dimensional lattice. By the way, here I'm going to be Euclidean. So this is really the total dimension. Okay, so two-dimensional lattice, and we are free to pick, say, the parameter s to be smaller than 1. Then we measure the critical exponents, and what we find is that these critical exponents, for the two-dimensional long-range Ising model with s less than 1, they are completely controlled by a Gaussian theory. So they are in some sense trivial. But then as soon as if I take s between 1 and a value here that is, say, around 1.7, then I actually do find some non-trivial, interesting new critical exponents, which are those that they characterize the long-range Ising universality class in 2 dimensions. And then as soon as I cross this dashed line, this value S star, which is around 1.7, I yet cross over to a new phase, in a sense, where the only non-trivial critical exponents are controlled by the 2-dimensional short-range Ising. So you see, this is the crossover transition. And what is interesting is that, in a sense, this interesting region, this interesting sliced potato, exists even in 1 dimension, in a sense that it is known since the work of Dyson that the long-range Ising model in 1 dimension has a non-trivial phase transition if you take, with non-trivial critical exponents, if you take s between 1/2 and 1, there is still a transition at s equals 1 with infinite correlation length and discontinuous magnetization. And then there is no transition anymore if you take s above 1. Just to give an idea, of course, the reason why there is no transition is because there is it's because the one-dimensional short-range Ising model doesn't have a non-critical fixed point, it doesn't have a non-trivial critical point. The only critical point of the 1D short-range Ising is 0 or infinite temperature, right? So in a sense, this is why this disappears. There is no transition. So I also want to mention that essentially now so this is the interesting reason we want to study, and it's possible to say give some perturbative description of the long-range Ising universality class that works, say, close to this line or close to this line, and that's what I'm going to discuss next. So let me start from a perturbative description that was known for a long time and works, say, above this line. So this is known from since the work of Fischer, May, and Nickel, and it's a non-local phi to the 4 theory. So we are used to the local phi to the 4 theory, right? That is the one that describes in the Ginzburg-Landau sense the short-range Ising universality class, okay? But here we have, rather than a local kinetic term, we have a non-local kinetic term, okay? So this non-local kinetic term, as you can see, I mean, this non-local kinetic term may look strange, but it's just essentially some fractional derivative. And you can just see that it comes from the Hamiltonian, right? If you try to approximate this with a continuum theory, these things get replaced essentially by these. Okay? So at lambda equal to 0, the theory is said to be generalized free, meaning that, yes?
Is there a discrete model that can model the non-integer d?
I don't know, but here we are not saying that it has to be. I mean, this quantum field theory in particular works for generic D in the discrete sense. I don't know. For the lattice model, I don't know.
Sure.
Yeah, I don't think so. Right. So at lambda equal to 0, the theory is generalized free. That means that if you just look at this term, it's just Gaussian field with some unusual dimension fixed by this kernel. So the dimension of phi is d minus s over 2. Okay. But this theory is a perfectly fine theory with correlation functions that satisfy Wick's theorem, so it's kind of free with unusual dimensions. And at lambda equal to 0, if you take s slightly above d over 2, then this interaction is slightly irrelevant, and it leads to a short RG flow that allows you to compute critical exponents just slightly above this line. Okay? Then this thing becomes strongly coupled as soon as you approach the other endpoint, the dashed line. So it becomes useless, right? If you are not comfortable with this non-local kinetic term, I just want to emphasize that you can think of this non-local kinetic term as being some dimensionally reduced kinetic term So if you take a local kinetic term in higher dimension and you dimensionally reduced it, somehow this gives rise to this non-local kinetic term. Okay, so you can also think of this theory as being some defect in some higher dimensional theory, where there is just a free massless scalar field. It's not going to be terribly important for us, but I was just wanted to emphasize it. So I was saying this theory is perturbative above this line, just slightly above this line, but is strongly coupled as you approach the crossover. But there is a different description that is conjectured to be dual, okay, that was found not long ago by Behan, Rastelli, Richkov, and Zahn. And so as I said, at the other end point here, the universality class is essentially that of the short-range Ising model plus a Gaussian sector that is decoupled. So in this paper, the authors found essentially a way to couple these two theories, and the way, the theory is, the way to couple them is very natural. If you assume you start with the short-range Ising CFT in D dimension, assuming that you have it, of course, then let's say that this short-range Ising CFT has a spin field, something that we call a spin field sigma with a certain dimension, then one can always construct a linear coupling to another generalized free field chi, okay? And is free to choose the coupling, the dimension of chi, such that this interaction is again relevant, just as you go slightly below this line. Okay, so in this, so indeed there is. So if you, in particular, if you choose the dimension of chi to be d plus s over 2, then this interaction is weakly relevant if you are just slightly below this line. This leads to a short RG flow, and then these authors check that indeed it leads to a perturbatively controllable fixed point. Okay. Again, of course, this description is weakly coupled here, but it becomes useless here. Okay. Now, here is the core of the point, right? The point. Yeah. So the case of the one-dimensional long-range Ising is a bit special, and the reason is precisely because, well, in this description we assume the existence. We must assume somehow the existence of some non-trivial short-range Ising CFT, because otherwise there is nothing to couple to. But in one dimension, we know that the one-dimensional short-range Ising CFT is trivial. It is not. There is nothing non-trivial there. So what is the status? On the one hand, so if we just recall what is the status of what we know about the 1D long-range Ising universality class, as I said, so there is a non-trivial phase. If you take S between 1/2 and 1, slightly above 1/2, you can use the phi to the 4th description I mentioned before because it's still valid. It's perturbative around this point, but of course becomes strongly coupled as you approach this crossover transition. There is no transition above 1, and so in a sense this is the analogous of the crossover point. And the question we ask is whether there exists a dual description of this that allows us to. This question we ask is whether there exists another dual weakly coupled quantum field theory for the long-range Ising model near this point. So this is the objective and our plan. So I'm going to focus now onto the one-dimensional long-range Ising model. We'll be particularly interested in this region. And the key idea is to realize, as we did at some point, that there exists a beautiful dual description of the one-dimensional long-range Ising model on the lattice. It's a dual description in terms of a Coulomb gas of kink and anti-kinks that alternate. This description is, we call it Anderson-Yuval and Kosterlitz model because of this. So it's a beautiful description. I'm going to review it and then review what is the yes.
Can you remind me why the description of the other case doesn't apply to one case?
One?
Yeah.
This one?
Yeah.
Because there is no one-dimensional short-range Ising CFT, right? If you take the one-dimensional short-range Ising, you just solve it exactly. You see that there is no non-trivial transition.
Okay.
Correct?
You are not
Yeah.
really interested in trying to seek a model.
No, I mean what I'm interested is I'm looking for the one-dimensional long-range Ising is non-trivial. Okay, so this is the one-dimensional long-range Ising, and so it is known that up to s equals 1 included. So the model has a transition with non-trivial critical exponents. Then above 1 there is no transition. So the question, but it's not obvious that the answer is yes, but the answer will be yes, of course. Otherwise, there wouldn't be here talking to you. So this is there will be a model that works and is weakly coupled there. Okay.
You're saying along that region, the long-range Ising model is also weakly coupled.
Yes.
Okay.
There exists a dual description where it is weakly coupled. Okay, so I'm going to review this beautiful model, okay, and then I'm going to spend some time trying to recast this model as a bona fide quantum field theory, and finally I'm going to try to convince you that it works, and I'm going to even use it to make some predictions. Okay, so let me review this model. So we are back to the one-dimensional long-range Ising model on the lattice, okay, and just because I want to do it, so this is the Hamiltonian, okay, it's the one-dimensional LRI, but I'm also adding some coupling to the short-range case, which I can do, okay, just to be general. So now the observation is the following. The typical ordered state, the typical state at low temperature is ordered. So that means that you find large domains with plus and minus spins that alternates, like so. Large domains with plus spins and minus spins. And of course the idea is that there exists a dual formula. You can rewrite this state, in terms of some dual variables that only account for the sign changes. So some domain wall and anti-domain wall variables, or kinks, anti-kink variables, these ones. So we can say that this is all plus, right? And then it becomes all minus. So we say that we replace this thing with a plus and with this thing with a minus, and so on, right? We do this change of variables. So then what is clear is that such an ordered state at low temperature contains very few changes of signs, so there's very few kinks and anti-kinks, and so which are therefore dilute. So that means that the kinks anti-kink provide some weakly coupled variable in this dual formulation. And notice that also by construction they must alternate, right?
Is there some characteristic scale for these domains?
I don't know. These so I don't know. The answer is I don't know. So now what Kosterlitz, Anderson, Yuval, and later Kosterlitz did was to rewrite exactly the partition function of one-dimensional LRI in terms of these kink anti-kink variables that I defined before. And it's an exact rewriting, so I haven't done anything in a sense. It's an exact rewriting. I'm just rewriting the partition function that corresponds to this, okay? And so this partition function takes the form of a Coulomb gas of alternating kinks anti-kinks. So what happens is the following. We have essentially a configuration with pairs of kinks. We can have say n pairs of kinks anti-kinks with fugacity G, okay? So we have the sum of all possible kink pairs. Then we can insert these pairs in any possible position, so we have the sum over their position, and this is the Boltzmann weight, which is, so the energy turns out to be, after some computation, but again, it's an exact rewriting, it turns out to be controlled by some potential, it has this non-local form, right? So this power law type of potential that depends on S in this way. And by the way, also notice that written in this way, when you take the limit where S goes to 1, you get a log
This
Yes?
curly S is the same as the previous S?
Yes. It's an exact rewriting. Right, so the point is, yeah, it's an exact rewriting. So in the limit where S goes to 1, you find a log, and this is why you call it's called Coulomb gas, because usually we're used to the two-dimensional Coulomb gas with log interaction. Anyway, so it's going to be a special case, because for us it's going to be an exactly solvable theory, which was not noticed before, as far as I know. Okay, so there are two couplings, the inverse temperature B and the fugacity of these domain walls. So then Kosterlitz computed the beta functions, okay, and so like if you try to plot this beta function to see what is what are the RG trajectories, you find this fantastic plot, in my opinion. So here on the x-axis you find, there is the inverse temperature, and here there is the fugacity. So what happens is that if you start at any point here in region 2, say, okay, and then you tune the temperature and the fugacity such that you are here in your lattice model, and then you just flow with the RG till the long distances, you end up in a phase where the fugacity is very big, the temperature is very high, and therefore there are many kinks, no? Because if the fugacity high, it means that there are many changes of sign, so there are many kinks. This is a symmetric phase, because overall the magnetization will be 0. If you cross this red line, you enter in a different region, region 1, where instead you end up at low temperature, at large distances, you end up in a low temperature phase with very small fugacity, so there are no kinks. This is a phase where where the symmetry is broken, because there are very few changes of sign. So you see this red line separates two phases with spontaneous symmetry breaking, driven by kink-anti-kink pair proliferation. It's a bit remarkably similar to the BKT transition. Of course, it's not the same, but it's similar. And moreover, from the explicit equation, one finds that so the whole diagram is controlled by a fixed point, where the fugacity is of order delta. The fugacity is over the square root delta. Delta is just the distance from 1 in S, so it's 1 minus delta. S is 1 minus delta. And that means that when we are close to 1, right, when we are just slightly below 1, still we have in the infrared some weakly coupled theory, right? And one can compute, for example, some critical exponents as Kosterlitz did, and what he found is that, for example, the RG is controlled by this critical exponent, which is the critical exponent that controls the two trajectories. There is one relevant operator, one irrelevant operator, but their difference in dimension is of square root to delta. There is this kind of non-analytic behavior. Okay, so.
And that fixed point is not a stable fixed point.
No, it's not a stable fixed point. In a sense that there is a relevant deformation. Yeah. Right. Now, so this concludes the review, and what I want to do now is to recast this nice model into a bona fide quantum field theory. So I'm going to do something like I'm going to give you the ingredients, okay? I'm going to discuss each ingredient, and then I'm going to put everything together and tell you that magically it works. And more or less, this is how I proceed when I cook dinner. I think it's fine. So ingredients. So the first ingredient is a one-dimensional generalized free field, a Gaussian field with a negative dimension chosen like so. Okay, well remember delta is 1 minus s. So I already told you about this one-dimensional generalized free field. We can choose it whatever dimension we want. In this case, it will turn out that choosing this dimension is what precisely reproduces the partition function that we expect. But just to be very concrete, this is the action, okay? It's just a mean field theory, Gaussian field. Now, next step, we compactify this variable. Partially, because, I mean, essentially because we don't want to have a negative, an operator with a negative dimension in the spectrum, but we can compactify it. We are free to do that. And of course, the compactification will involve some dimensionful variable b, okay? But it's not a big deal. What happens is that after compactification, the spectrum will be discrete. So there will be the identity, the phi does not belong to the spectrum, but derivatives of phi are well defined, and also exponentials of phi are well defined. Even though I'm not claiming that these are scaling operators, so you shouldn't be worried, in my opinion, but these are the only things that you can, and then products of them. That's the only thing we can write down. So the observation now is that, so let's focus for a moment on this type of, I would like to call them vertex operators. So the first observation, but you have to believe me, is that if you now compute the correlation function with alternating vertex, anti-vertex, vertex, anti-vertex operators, so 2n of them, with charge 1, minus 1, 1, minus 1, blah, blah, minus 1. So you know how to compute this correlation function because it is evaluated in a free theory, in this generalized free theory to be precise. And the statement is that this object is just a property of Gaussian fields, right? So this object exponentiates and recreates precisely the Boltzmann factor that appears in the partition function of the Boltzmann weight that appears in the Anderson-Yuval-Kosterlitz model. Okay, this is done, of course, very carefully in our paper, but so I mean, it works, okay? And it works precisely because we have chosen the dimension of phi to be minus delta over 2, because then, you know, this potential here, it's essentially the covariance of phi, right? So you can think essentially of this, this tells you that you can think of this vertex operator in x1 as being creating a kink here at x1. This one is creating the anti-kink at x2 and so on. So it's clear that we have to perturb by the original GFF in order to get something non-trivial. We need to perturb the GFF by vertex operators. So we have to include something like this, right? So our action is going to include something like a sum of V1, V minus 1, okay? But it's not quite the end of the story. It's not, yeah, we are not even close. So the one very crucial point is that, as I mentioned, these charges must alternate. So in the Coulomb gas model that comes from Anderson, Yuval, and Kosterlitz, we have that these kinks and anti-kinks, they alternate by construction. In our language, that means that when you have two adjacent vertex operators with the same charge, well, then your correlation function must vanish. Whatever, I mean, it must vanish, and it must vanish somehow off shell, right? And the idea, I mean, in order to impose this condition of off shell, so the idea is that you don't just perturb the GFF with V1 and V minus 1, but you also couple to some Spearman alpha algebra, right? This is just a combination, an important combination of Pauli matrices, sigma x plus I sigma y, such that they square to 0. If you do so, right, now every time you lower in perturbation theory, every time you expand the exponential and you lower g, you see that, I mean, of course, by construction, you only get correlators with alternating V1 and V minus 1, okay, by construction. But then if you write this interaction, then you also generate another interaction, because when you fuse this operator with this one, I mean, you necessarily generate another coupling, which is precisely this, okay? So it's the derivative of phi times the third Pauli matrix. And okay, so of course I'm kind of constructing this action a bit out of I mean, it's a bit unwavering, but so a posteriori one can check that this theory is invariant under certain symmetries. For example, there is parity is a 2 symmetry. Okay, I'm going to perhaps say more later, but And there is a global U1 shift symmetry that acts both on phi and on these matrices. And this theory is natural under these symmetries. There is nothing else you can write. Okay? So now the final observation is that now, right, so this is the partition function at the end. So I'm just calling, yeah, it's written here. So I'm just I'm just giving some names. So this is essentially this object, right? So I'm just saying that, so this is the partition function, is the trace of the path ordering exponential of this, right? And you can think of this as being somehow a defect line. So it's almost like, looks like a Wilson line, essentially. Right? Now, so very good. So now at this point, you can forget about whatever I said. I give you this. As I said, everything is computed in a free theory, so you know how to compute correlators, and one can just check that taking this partition function and expanding order by order in G for every value of H, you just reproduce the partition function of Anderson, Yuval, and Kosterlitz. And in particular, you find that the coupling G is exactly equal to the fugacity of the statistical model, while essentially H is related to the inverse temperature in a specific way, okay? And I also want to emphasize that although this action already appeared in the, in fact, this action already appeared in the context of some bosonized version of the Kondo model, so it has been related to some impurity problem, but they were always considering some case with H equal to 0. So this thing was not included, and as far as I mean, and the point is that this interaction is really necessary for the correct RG treatment. If you don't insert it, you're not going to be able to renormalize the theory in perturbation theory.
Sorry, can you say again, what's the role of big L?
Oh, yeah, this you can take, you can just take it to infinity at the end. You can just take an infinite line. I'm just, so it's an infrared cutoff, but you can take it to infinity. Yeah. And, okay, so this is a bit of a technical point, but I just want to say that now, let me tell you the following, just to be quick. So there is path ordering, and as people working with Wilson lines know, and perhaps everybody else as well, but for us it was hard to realize until we actually read this paper. So when you compute correlation function, you have to be extremely careful, because now you are computing correlation functions of, say, local operators inserted along this line. This defect line, it's this, right? So you can visualize it as like, yeah, just like, so you have to attach the line, so you're computing along this line, so you're attaching the line to each of these operators. And so there is, for example, in this case, you can see it, when you have this Wilson, this kind of defect line, you have to keep track of the dependence on the insertion point, x2, that comes from both sides, so also from the defect line. And the right way to take into account this dependence is to introduce some covariant derivative, okay? And the key point is that because of this covariant derivative, you can see that, for example, even the nice, sigma 3, which I introduced it as a Pauli matrix, in fact, it behaves, it has a subtle position dependence, and so it behaves really as an operator. We should think of it as an operator, and in particular, this equation is, if you want, you can view it as an equation of motion. Will tell you that sigma 3 can get an anomalous dimension, and in fact it will, as I will describe. So it's important that now, because of path ordering, for example, I told you this looks like a total derivative, but it's not, because there is path ordering. Here you can tell what am I doing. I'm considering matrices. I'm telling you that they transform, they take anomalous dimension, but they are not really matrices. I mean, because of this path ordering, and I think the right way to view it is in terms of these derivatives.
Why do you call this whole, so in your case, you call the whole line to be the defect?
I'm just saying that it's like you are in one dimension, but there is you're in one dimension, and there is a precise prescription to compute the correlation functions with these. And everything is path ordered, so it means that you first insert the line, then you insert the operator, then you insert the line, then you insert the operator, and it's like a bit like computing operators along a Wilson line, computing correlation functions of local operators along a Wilson line. You have to be careful. So, okay, I'm going to be very quick here. So now I give you...
Are you going to insert some boundary condition changing operator?
These are like sigma 3, you can think of it as a boundary condition changing operator if you want. It's not, okay, but it's like, it's something that has to be attached to this D, right? So sigma 3 does not commute with this defect operator D. It's a defect. It's really the defect operator. It's not like
D is non-local. Well,
yeah, it's not a local defect operator. D is not a local defect operator. That's what I'm saying. I'm just saying that you can think of if you compute this partition function, you can think that you are computing some partition function in the background of a defect line. And when you compute now correlation functions of operators in the background of this defect line, you have to be careful where you insert operators, right?
In principle, you could also add the matter, quadratic matter, and write a coupling that implements the path ordering, right?
That's right, precisely. For example, there are dual descriptions of this model that involve some fermionic bosons in one dimension or something like this that implement the path ordering in a sense that their correlation functions are theta functions. And so at the end, there is an equivalent representation where there is no path ordering. It's just implemented from the green function of the additional matter. Indeed.
Is there any sense in which you can think of this as like arising on the boundary of a 1 + 1D compact boson or something like this?
Yes. Can I? Yeah. Yes. Absolutely. In fact, this is how we understood it first, but it's at the end it's perhaps not the most useful way to see it. I don't know, but I'm going to tell you. So anyway, so now you have. I think there is a theory. There is a well-defined prescription to compute observables. One can just do standard RG. In quantum field theory, we know how to do it, and for example. One computes the beta function, and one of the reasons why quantum field theory is very nice is that it's kind of it's easy to systematically implement RG. So as far as I know, so one gets the beta function with even an improvement term of higher next reading order. So these are exactly, they are the beta. This is the beta function of Kosterlitz. So we find the same RG with the same fixed points, of course. And when we linearize around the RG, of course, we recover the spectrum of the exponents of the RG plus some improvement that comes from this term. But I mean,
you can compute it at any order.
Well, no, in perturbation theory, order by order, assuming that the thing is that it's so. This is the beta function. You do it in perturbation theory, then you see that the fixed point is small if delta is small. So you see, and then so in a sense, at this point you have some epsilon-like expansion, epsilon-like expansion. But you can also go and compute of coefficients. I mean, it's just to scare you, but it's okay. I mean, it's just that we know how to compute correlation functions in a quantum field theory. It's very systematic. So there are some symmetries as we discussed. So now I just want, so now everything works in a sense that we reproduced Kosterlitz equations and we are happy. I just want to give further evidences that we are actually looking at the same theory. Okay, so what are the UV symmetries, for example? So from the lattice model, we know that there is a Z2 of split of spin flip. So this is the lattice sigma. There is a Z2, a global Z2 of spin flip, and there is also parity. Okay. So indeed, one can find such symmetries also in our model. So there is a Z2 that acts by flipping the spin of phi. I recall that this phi is this compact GFF, okay? But it also acts on the matrices. So there is a parity transformation that acts also on the matrix, and there is this U1. It's a shift symmetry. Our theory is obviously symmetric under the U1, this U1 shift symmetry, as long as you also change you also transform the matrices, and that's fine. So the only problem is that, in a sense, this theory has too many symmetries, right? Because like the 1D long-range Ising model is not supposed to have this U1 symmetry, this global symmetry. If you can compute the spectrum of the 1D LRI in the other near the other description that I shown, the non-local phi to the fourth, and there is no such a symmetry. So the claim is that you know so this quantum field theory seems perfectly fine, but then like if you really like the 1D LRI is really a sector of this symmetry of this quantum field theory, that is the sector that is actually neutral under this U1. And then one can go further and compute, well, actually, one can try to list all the operators and try to see what is, whether, so we expect indeed that now we expect that there is a certain duality that works. So we expect to have two equivalent descriptions of this 1D LRI, one as a non-local phi to the fourth, and one as this theory that I presented. And we just go over the spectrum to check what if things can match. And right, so the first operator is the identity. It has dimension 0, and it's of course even under everything. So in the non-local phi to the fourth theory, it's of course the identity operator. Then there is sigma 3. This operator sigma 3, as I said, it's an operator because of the path ordering, so it's not really a matrix, right? But so when you compute when you compute its dimension in perturbation theory, it turns out to be exactly delta over 2. Okay, and the fact that this number does not receive higher order corrections, essentially because of the equations of motion. So you can compute the Schwinger-Dyson equation and see that the dimension of this operator is protected. And so this operator is actually identified with phi in the other description. So this is the mean field theory phi in the phi to the fourth description, whose dimension is fixed to be exactly d over 2 by the kinetic term. And the reason why in this other description this number is protected is because it's a non-local kinetic term, so it cannot get renormalized by local interactions. Okay, perhaps this is just a fact, right? So if you have a non-local kinetic term plus a local interaction, then the local interaction can do whatever, but it can certainly not renormalize the non-local kinetic term because the UV divergences are local. So there is no way to do it. You can keep going. So there is so there are these two operators that we computed. These are not protected, and we expect, for example, to be related somehow to phi squared and phi to the fourth in the other description. And then we go on. For example, there is this operator. This operator turns out to be of dimension 1 plus d over 2. And this operator is related to the derivative of phi in the other description. And it's just, again, this operator is exactly the descendant of sigma 3. So we really see that this covariant derivative is a very important object, because if we just think of this object as cannot be written as a total derivative in any possible sense of some operator. So at the infrared fixed point, it cannot be a descendant in the usual sense, but it is equal to the covariant derivative of sigma 3. So it is a covariant descendant, and it's very important to keep it in mind. So we computed these using the quantum field theory I presented, okay, and these are some results. More results can be found in our paper. But the point I want to emphasize is that so everything seems to be in a sense, consistent with the dual description. So there were two descriptions, and the spectrum of protected operators that we expect match on both sides. And we can also obtain these results by a completely different method that does not assume anything of our quantum field theory except the symmetries. So if we assume that our model flows to an infrared fixed point that is governed by conformal symmetry with the global symmetries that I presented, so in particular, well, Z2 and parity, right? So then, so then there are, I mean, this is a conformal field theory with a certain symmetry. It must satisfy some consistency conditions, the crossing equations, the bootstrap equations, and one can solve them analytically in a perturbation theory for small delta, and finds to recover precisely these results. So it's a completely independent check. Okay, and then I just want to conclude by saying that there is so the special point. There is a point that, so if we set s equals to 1, this is a special solution. You can see it from here. S equals 1 means delta equal to 0. So from this beta function, you see that the fugacity is 0, and the temperature, the inverse temperature, is 1. So, like in the lattice, in the Anderson-Duval-Kosterlitz model, this is just some special case where the potential becomes a log, but it's not. There is no hint that it's an exactly solvable theory, in my opinion. Instead, what we find is that thanks to this description, this quantum field theory description, what happens is that in this limit, so we just kill the interaction, right, and we recover the just the theory of a compact GFF with 0 dimension, because well, the dimension of phi was minus delta over 2, so it becomes 0.
Sorry.
Yes.
One quick question. Why to say 1 minus?
Because my theory works for S between 1/2 and 1, and not claiming anything about.
So you cannot choose 1 plus, is right?
I mean, if you want it from the point of view of this theory, it becomes a complex fixed point.
Oh, okay.
Right? Because it's just, you know,
Yeah,
the fixed point is this. So if you take delta to be negative, it becomes complex. But I don't know if it is related to LRI. So it is. The claim is that it is related to LRI from if you approach it from the left.
Okay, thank you.
Yeah, and so the only thing I want to emphasize at the end is that this limit is a limit that leads to an exactly solvable theory, which is this compact GFF plus a spin 1 alpha algebra. So integer spectrum, beautiful. Of course, you have to restrict to the U1 neutral sector, but it's computable. And just to address your point, of course, now if you compute the kernel, I mean, the propagator of this is a log, and you can view it as this as the boundary value of some free compact boson in 2D at the self-duality radius. And now you can wonder perhaps what happens for a more generic value of delta. And again, there is a correspondence, but it again becomes, so as I mentioned, there is this interesting point of view on the long-range models as that can be viewed as defects in theories with free fields. So the long-range Ising can be realized as a defect on a theory of a free massless scalar field, and this is what we are, in a sense, rediscovering. So, in the case where delta is equal to delta is not 0, so S is not 1, you have essentially some fractional codimension. That's the issue. So the model is not more physical, seen as a defect in that sense. Okay, I'm okay. I just want to spend some time in just tell you again the conclusion and discuss some further future directions. So the point is that there is this nice sliced potato thing, and this is a beautiful, interesting region to be explored, much less explored than the short-range Ising, of which we know a lot. And so there are two nice and dual perturbative description. One found by these people that works pretty well, that works well in this near the crossover, and another one, the non-local phi to the fourth, that works in the opposite in the other region. I mean, in the opposite regime, right? But this keeps working when d is equal to 1, but this one instead is not really well defined when s is equal to 1, and d is equal to 1. Of course, it's not supposed to work. I mean, the authors do not claim that it works, of course, because it assumes the existence of the short range Ising CFT in the corresponding dimension. So essentially, our work was to, in a sense, fill this dot literally to try to understand a bit whether there exists a dual formulation of the model that is weakly coupled here. And at the end, if you compare, it's like essentially you have to replace. So the idea is that you have to replace rather than coupling. If you compare with what happened in higher dimension, where you couple the spin field sigma with chi, here we are not really coupling the spin sigma. I mean, sigma is not an operator. Is not really an operator. It's some operator of some topological quantum field theory, which is just this spin 1 alpha algebra. There is also the Gaussian sector, and the coupling, the only coupling that can be consistent with the symmetry is this exponential, rather than just a linear coupling. So if you want, there is some. But anyway, so whatever is if there is there might be some other better presentations of this theory, but it works as far as we can say. We used it to compute and check critical exponents of Kosterlitz. We recompute the same object by a completely different method that does not use the quantum field theory or the Lagrangian. It's the bootstrap. Everything agrees, and I think we can call it a day. And so the future direction is the following. I want to. Now, this is perhaps more like a discussion, but so I think I'm very excited about exploring more long-range models, because these long-range models they have these nice features like crossover transition from long to short range. There are dualities because in the sense that we like infrared dualities between weak and strong coupling descriptions. So I did some recent study on some, we kind of constructed with Connor and Fanny Eustachon and Dario Benedetti, we constructed some example that generalized the long-range Ising model to long-range minimal models. And again, they are nice type of models that one can study. And the point is that now, what are the tools that we have that are available? So in the case of the 1D long-range Ising, we do have perturbation theory, but there are still we can try to do some Monte Carlo simulations. We can try to do the bootstrap, for example, and they are all bootstrapable theories, but there is a lot to be done. And I think for the bootstrap, in my experience, it was very, very crucial, unlike in the story that I told you today. It was very crucial. I mean, not in the sense that it was fundamental, but it was important, it was useful. Useful is the correct word, sorry. It was very useful to think of the long-range Ising model as a defect. Because, like in some sense, in the presentation of the model as a defect, there are many non-perturbative constraints that just emerge very nicely, and when we did we did the bootstrap for the long-range Ising model in this paper, and using this defect type of description, it was very nice. But of course, there are also connections with experiments, but perhaps. And so I think this is also an interesting point, and yeah, I don't know. It's just let's long range and let's make it more defective. Okay. So well, this is all what I wanted to say. If there are no other questions, I think we can stop here. Let me let me just let me just thank the organizers. I think they deserve. I mean, the institute and the organizers. Thank you.
Let's thank Edoardo then again. Are there more questions?
Wanted a better sense of how to think about the sigma 3 as a quantum field. I mean, it's just the third Pauli matrix. How is there a? You make it a function of time.
Except that it's not, right?
Path integral, or?
It's not. It's not a. It looks like a Pauli matrix, but it's not. I mean, because like. So there is a way. So if you want, there is an equivalent presentation of this model in which you, rather than having matrices, you have some additional dimensional zero operators that propagates from scalars with that anti-commute. So it's you can view it as a bosonization, if you want, of this model. But the thing is that like so there are better ways of seeing it, such that you don't have to deal with the path ordering, you don't have to deal with the fact that the counterintuitive fact of the thing that you have just mentioned.
Is that done precisely somewhere? Or?
Yeah, so in the appendix of our paper, I think it's done more or less. I mean, I'm not even sure, but I think yeah, we mentioned it, and so
for the S=1 case, we
yes,
do it exactly,
but
for smaller than 1.
Yeah. Yeah, certainly for S=1, it is done. But Chris, just to emphasize, I mean, I completely share your viewpoint. It's a bit counterintuitive, but nevertheless, I mean, at the end, these objects, they should not be taught as matrices. They are, they do depend on the insertion in a very subtle way. So they are really fields. They are fields with indices, like spinors.
There's a completely Lagrangian description of qubits, actually. It's sometimes called the cojoint orbit method. But yeah, you can write down a Lagrangian, which when you quantize it gives you a finite dimensional Hilbert space. And I think that's probably what.
Yeah, they are like spinors, no? So except that they start with dimension 0. That's the thing. Like their classical dimension, if you want, when you write it in the Lagrangian, the classical dimension looks like, well, they're dimension 0, so they're just C numbers, but they are not. So that's why it's perhaps confusing. That was confusing for me, and it's not like something that we. I mean, sorry that I say it, but it took us some time to realize that. I think they were like I want to emphasize that for us it was revealing, understanding this, well, discovering this way of doing things through this. Covariant derivative that Lorenzo and collaborator used very naturally. So that is what clarifies everything, in my opinion. It clarifies the structure of descendants, primaries at the infrared fixed point. It just tells you that this sigma 3 has a non-trivial covariant derivative, so there is some subtle dependence. It's really an operator.
More questions?
Is there something that you can do on the lattice that like puts back the U1 non-invariant operators that you projected out?
Yeah, good question. I don't know.
Another question.
Sorry, one possibility is to, if you try. So I think this U1 neutrality comes. This U1 invariance, in a sense, comes from it's really due to the constraint. The fact that you cannot have the constraint of alternating charges. If you construct a model where the charges are allowed, the kink and the anti-kinks are allowed to somehow not alternate, then you will probably break this U1.
I mean, you can also probably model this by thinking that you've coupled to a 1D U1 gauge field on the.
That's right. Yeah.
Another question I had was, I mean, should I think that in general, when I have a 2D CFT with a boundary, I can alternatively interpret the boundary as furnishing some kind of 1D long-range critical thing?
I think when you have some, I think so. I don't know if it is useful, but you can do it in a sense that you know it very well. Like if you restrict to the, if you have a defect, a theory with a defect, and you restrict on correlators on the defect, the theory will not be local. Yeah. So in general, you can expect all sorts of things.
Right. I guess I'm just curious if there's other lattice models like the long-range Ising model that you might try to engineer sort of 2D boundary CFT descriptions of.
Like some percolation, perhaps. Some percolation, some long-range percolation theory. Yeah, I think that can be done. Yeah, let me also tell you something quickly related to this. I think in the open, this is not very precise, but in the open quantum system community, when they have some open quantum systems, right, and they want to study the evolution, of this quantum system, but they want to somehow, well, they cannot use unitarity because it's not unitary. So what they do is they couple this model to a bath, right? The bath is usually some theory with some simple dissipation, some simple law, some free theory, and this is a bit what you are proposing. So it's a bit. So the idea is that then the whole system is unitary. You can derive the evolution using unitarity. Once you restrict to the line, it will look like an open quantum system, and but you really view this model as some non-local object embedded, that becomes local when embedded in some bigger theory. Negative time. Wow.
I want to ask, so how do you compare your model to this 5-4 model in the embedding space? If you embed your long-range Ising using the Cavalieri-Silvestro tree?
Yeah, it works. I think it also works there. It's very similar.
That model is a transition from the Gaussian model to the long-range Ising model, but you're considering more the opposite.
So if you want to view this model here as a defect theory, you have to. The point is that now the Gaussian field that you have is compact, so it's not really a physical field. So your bulk field is not really phi, but it's rather the derivative of phi. But then the Caffarelli-Silvestre trick works, I think. So you have some phi that is some derivative of phi, some big phi that is the derivative of phi, somehow, in the bulk. I tried to do it in some appendix, by the way, but perhaps you will find that it's actually totally wrong. Hopefully not. But I did it. Yeah.
U1 symmetry. You had a slide a few back about where you defined this one. What was the capital A?
Oh, it's any of these matrices. So it's any Pauli matrix. Or it's, I think, either sigma 3 or it's one of those simple-looking matrices that are actually operators. Means that, for example, here it just means that you have to take the sigma plus and conjugate it in this way by the sigma 1, the sigma minus, etc., the sigma 3 idem. So, sorry.
I noticed that naively, right? Your vertex operators break this U1, but I guess you've restored it by allowing the...
Precisely.
Okay.
Good. If there are no other questions, let's thank Edoardo again.